Hello, my name is Giovanni Guizzo. I'm a research fellow at University College London, and today I'm going to present to you the paper Comparing Fuzzers on a Level Playing Field with Fuzzbench. I co-authored this paper with Dario Asprone and Federica Saro from UCL, and Jonathan Metzman and Abhishek Arya from the Google Open Source Security team. So, fuzzing is a commonly used technique in an industry during the testing process. The main goal is to feed automatically generated inputs to the target program in order to make it crash. In spite of its popularity, previous work did not always follow a shared or sound empirical methodology to assess and compare fuzzers. Each paper that proposes a new fuzzer uses an ad hoc evaluation framework, making it a hard task to assess the true quality of the fuzzers. In fact, Cleese et al. In 2018 published a meta-analysis on the methodological soundness of 32 fuzzing papers, and the results are very alarming. There is not a single paper that shares the same methodology. Moreover, those papers fail short in many methodological aspects. Our work aims at addressing this gap in the literature. With that in mind, the main goal of our work is to evaluate a set of relevant and widely used fuzzers in a robust and fair way, mainly addressing the shortcomings unveiled by Cleese et al. In their paper. That includes the usage of many well-known and state-of-the-art fuzzers as opposed to comparing a given fuzzer to a single baseline, using real-world software as benchmark as opposed to artificial benchmarks or artificial bugs introduced in real-world programs, introducing measures for assessing the bug-finding ability of fuzzers rather than only measuring code coverage or the inflated number of crashes, performing many repetitions of the fuzzing campaign to cater for the inherently stochastic nature of fuzzers as opposed to running them only once, and finally, performing sound statistical analysis rather than reporting raw results only. For that purpose, we decided to use Fuzzbench, a state-of-the-art fuzzing benchmarking service developed by Google. Fuzzbench includes a diverse set of fuzzers, many real-world programs, real-world bugs curated from a bug tracking system, a crash deduplication mechanism internally used by Google in their fuzzing processes, and a reporting tool. Fuzzbench fits perfectly to our purposes, which led to the collaboration between UCL and Google to realize this work. We collaborated in order to extend the default dataset used by Fuzzbench, as well as introduce measures to capture the fault revealing ability of a given fuzzer. These and other results of our investigation were incorporated into Fuzzbench and can be used by other researchers. So, in summary, the main contributions of this paper are a large-scale and rigorous empirical study comparing many fuzzers on real-world software with real-world bugs, a manually curated ground truth suite of real bugs for open-source projects. Open source code and data are made available in Fuzzbench and our online appendix to allow for reproduction, replication, and extension of our work. If you would like to use Fuzzbench or to check out our online appendix, feel free to access those links or to contact me via email. I will be more than happy to point you to the right direction. So, without further ado, let's dive deeper in our empirical study. We assess fuzzers based on three criteria: effectiveness, which measures the fault revealing ability of the fuzzers; efficiency, which measures how long it takes for a fuzzer to find a bug and how long it can keep finding bugs during the fuzzing campaign; and bug types affinity, which measures whether specific fuzzers can find specific types of bugs more than others. We also perform a correlation analysis of coverage versus bug revealing in order to verify whether one can be used as a predictor for the other. With that said, our experiments are aimed at answering 4 research questions. RQ1 is concerned about the effectiveness of the fuzzers in finding bugs, RQ2 is concerned about their efficiency, RQ3 is concerned about their affinity for bug types, and finally, RQ4 guides the correlation analysis between number of crashes and code coverage. So, in order to run the experiments presented in this paper, we manually created a set of real-world bugs extracted from real-world open-source projects. In order to exercise the fuzzers with various difficult-to-find bugs, we purposely selected 12 programs from the OSS Fuzz bug tracking system. OSS Fuzz is a fuzzing system used by Google encompassing a wide variety of open source programs and a history of revealed bugs. Hence, with such information, we were able to create a bug ground truth, let's say, using all the bugs revealed by OSS Fuzz in the past. To be more specific, we selected projects with the largest number of bugs. In this case, we found the buggiest version of the project by mining information about all of their versions. Each of the selected program versions has from 17 to 49 known bugs. We also selected projects with hard to find bugs. We performed this selection by analyzing the lifetime of the bugs in the programs, in the bug tracking system for the programs, and selecting the versions of that specific program with the most bugs that took the greatest amount of time to be found. Finally, we also selected programs uniformly at random from a set of mined programs for an unbiased analysis. In the end, we obtained a diverse dataset with multiple levels of difficulty and different number of crashes. These programs are all integrated into FuzzBench and online, ready to be used. As for the fuzzers, we used the 9 fuzzers implemented with FuzzBench at the time. They are AFL, AFL Fast, AFL++, AFL Smart, MOPT, FairFuzz, Entropic, LibFuzzer, and HongFuzz. These fuzzers can be divided into 2 main families, the AFL family and the LibFuzzer family. Each constituent fuzzer is derived from the main fuzzer of the family. The only exception here is HongFuzz, which is an independent fuzzer, developed independently from those families. Each fuzzer is executed in our experiments for 23 hours in each fuzzing campaign, and for at least 20 independent campaigns to cater for their stochastic nature. In order to analyze the results, we developed a rigorous scoring system based on many measures, independent runs, and statistical tests. First, we analyzed the number of unique ground truth crashes, or GT for short. That is, the number of known bugs in our created ground truth. By unique crashes, I mean after the deduplication process, as many different crashes can relate to a single bug. Second, we analyzed the number of additional crashes, or just AC. In other words, the number of crashes found by the fuzzers that were not in our ground truth. This can happen for several reasons, such as the bug not being found by OSS Fuzz in the past, the natural performance improvement of the fuzzers over the years, by having better hardware than when the bugs were reported in the OSS Fuzz bug tracking system, or due to differences in the deduplication algorithm. Nonetheless, it is important to not discard such crashes and include them in our analysis. Finally, we analyze the unique distinct crashes, that is, the sum of all unique crashes. Here, instead of reporting the raw number of crashes, we instead report the ranks of the fuzzers adjusted for statistical equivalence or statistical difference. For that purpose, we use the following equation, where NR is the natural rankings of the fuzzer for a given metric. For instance, the natural ranking of a fuzzer that found 10 bugs is 1, when for another fuzzer that found 5 bugs is 2. So this is the natural ordering, the natural ranking of those fuzzers. And then we average those ranks towards all the equivalent fuzzers according to a specific statistical test analysis. So in summary, this equation computes the average ranking of a given fuzzer while considering fuzzers that do not show statistical difference at the same rank. Hence, if a fuzzer is statistically equivalent to another fuzzer, they will probably have the same rank, ignoring negligible differences in their number of revealed crashes. This is done to cater for the statistical differences that can arise from multiple repetitions and in order to provide a fairer comparison between the fuzzers. For the statistical analysis, we use the Kruskal-Wallis test for computing p-values within a given benchmark and Friedman test to compare p-values across different benchmarks. Because those two tests can only tell us whether there is a difference or not, we have to use the Vargo-Delaunay effect size to compute the magnitude of those differences. because there are many comparisons to be made, we report only the linear and quadratic effect size scores. In summary, these scores assign a point for each favorable large, medium, small, and negligible effect size comparisons amongst the fuzzers. So, going to the results now, for RQ1 regarding effectiveness. This table summarizes the results for each fuzzer across all benchmarks. In general, HONGFuzz and AFL++ perform similarly for all types of bugs, obtaining the best ranks overall according to the Friedman test. HONGFuzz also obtains the best ranks for almost all cases in the effect size rankings, but they just rank for additional crashes. AFL++ takes the second place overall, having a better adjusted ranking when compared to HONGFuzz for additional crashes. If we look at the fuzzer families, the AFL family performs a little bit better than the LibFuzzer family overall. So, if performance is the goal of the fuzzing campaign, then we recommend either HONGFuzz or AFL++. For answering RQ2, we computed the timestamp for the first and last crash found on average. This information might be interesting for testers who want to find a bug as fast as possible, or who want to keep finding bugs throughout the fuzzing campaign. FairFuzz and AFL Fast consistently rank amongst the top half of the ranks, whereas Entropic, LibFuzzer, and HONGFuzz rank at the bottom half for all cases. The interesting observation here is that although HONGFuzz ranks at the top in effectiveness, it is not so efficient, meaning that it starts to find bugs late in the fuzzing campaign and tends to stop finding bugs early. So if efficiency is the main goal of the fuzzing campaign, so the tester should use FairFuzz and AFL Fast in those cases. For answering RQ3, we grouped the bugs together based on their type. The image you're seeing here are the bug types in each bar cluster, and each bar is a different fuzzer. The first observation here is that most common types of bugs are integer overflow, divide by zero, and heap buffer overflow. Also include the undefined shift here, but those are not interesting. So for integer overflow, divide by zero, and heap overflow, they comprise approximately 28%, 13%, and 10% of all bugs found by all fuzzers. Another interesting observation here is the disparity in number of divide by zero bugs found, from which HONGFuzz found 84 bugs and FairFuzz was able to find just a single bug of that type. Moreover, AFL++ and HONGFuzz found almost 35% more integer overflow bugs when compared to other fuzzers. Aside from those two cases, we have not observed other specific affinities from the fuzzers. Finally, we analyzed the correlation between the source code coverage and bug revealing ability of the fuzzers. In summary, the overall correlation across the entire data is very weak, with a Spearman's rule of 0.1. However, when we grouped the data by benchmark, we could find strong correlations for a few programs, but not so strong correlations were observed when we grouped the data by fuzzers. This indicates that, not surprisingly, the analyzed correlation depends more on the benchmarks than on the fuzzers being used. This highlights that code coverage is not always a reliable metric to measure the bug revealing abilities of fuzzers. One should instead use number of bugs found or other metrics that can better capture this goal of the fuzzing. So, in conclusion, we extended FuzzBench with a set of new programs curated for diversity in difficulty, number of bugs, and accompanying a ground truth list of bugs. We performed an empirical evaluation of 9 fuzzers and 12 benchmarks with 20 repetitions and 23 hours each campaign. We found out that HONGFuzz and AFL++ yielded the best effectiveness among the fuzzers. We also found out that FairFuzz and AFL Fast are the most efficient ones. We unveiled a few bug type affinities for AFL++ and HONGFuzz, and finally we found out that the source code coverage is only strongly correlated to bug revealing ability in very specific benchmarks, and, in general, cannot be reliably used as a proxy for that purpose. As future work, we intend to keep extending FuzzBench to accommodate new fuzzers and even more diverse benchmarks. Finally, we will also investigate why a few bugs are not found by specific fuzzers and what causes other fuzzers to find more bugs of a specific kind. Thanks for watching, and if you have any questions, please do not hesitate to contact me. Cheers!